In my Structural Engineering Made Simple series, today I would like to talk about design of reinforced concrete flat slabs. This is part 1 of a two-part series and will focus on one-way slab design. Please take a moment and read the disclaimer at the bottom of this slide before we continue. Flat slabs are considered thin structural members that are supported by beams and columns. Depending on their two main longitudinal and lateral dimensions, they are classified as either one-way or two-way slabs. They are also referred to as one-way or two-way floor constructions. This video explains the design for one-way slabs. In general, the process includes a design for appropriate thickness for the slab, reinforcement and pertinent code requirements for minimum steel and bar arrangement, and shear resistance requirements. These are pertinent references used in the preparation of this video. The ratio of the longer dimension L2 to the shorter one L1 is called the aspect ratio and is used in the designation of one-way versus two-way slabs. This figure shows the configuration of a flat slab used in a floor system. As you can see, the reinforcement in the L1 direction has a spacing of S1 and the reinforcement in the L2 direction has a spacing of S2. The thickness of the slab is H. Generally, when L2 over L1 is larger than 2, the slab is one way spanning along L1, with the main reinforcement in L1 direction and a minimum amount of reinforcement in the perpendicular direction. When L2 over L1 is less than or equal to 2 and larger or equal to 1, the slab is two-way with main reinforcement in both directions. Notice that the reinforcement is in the form of a grid. Here are the general characteristics of a one-way floor slab. As indicated, the reinforcement is in the form of a grid. The main reinforcement refers to the bars in the direction when bending moment occurs, and flexural design must be used to determine the amount of steel needed. For design in one-way slabs, only 1 foot of the slab in L2 direction is considered, as shown in this figure. Therefore, the design is done for a strip of 12 inches of width. Notice that now in this figure, in the L2 direction, we have shown the bars designated as a minimum steel. Sometimes it is also called the temperature steel because they are used to prevent cracking because of the variation in temperature. A cross-section detail for a one-way slab, therefore, for design will look like the following. Notice that we dropped the subscript and use S for the spacing and L for the span length in subsequent slides. The main tension steel AS has a spacing of S and it has a unit of square inches per foot. And B is always equal to 12 inches. Depending on the slab thickness, the slab may be made up of only one grade, two grades, or a grade alternatively placed at the top and bottom in places of negative and positive moments. Here are some examples of reinforcement placement in a one-way slab. Remember, a slab spans in L direction. In this one, the grade alternates at the top and bottom for negative and positive moments. The bars shown perpendicular to the plane are the minimum amount of reinforcement in the L2 direction. And notice that there is a designation for Ln, which is called the clear span, versus L, which is the theoretical span length. In this detail, the main steel AS for positive moment is bent up and gone over the support to provide the main steel for negative moment. This figure shows separate grades at the top and bottom, applicable generally for thicker slabs that can accommodate two grades. Usually the top and bottom grades are based on the minimum steel. Additional bars are added at the top over the supports and at bottom at the midspan to meet the required areas of steels in these areas, as shown in the plan view. You notice that we had additional steel at the bottom for positive moment at the midspan, shown with the dash bar, and a solid bar shows additional steel at the top for negative moment over support. Here are the notations. AS is the area of longitudinal tension steel. B is the width, which is always equal to 12 inches. H is the slab thickness. D is the distance showing the location of a steel measured from the center of tension steel to the extreme concrete compressive fiber. F prime sub C and Fi are the concrete compressive strength and the steel yield strength, both in PSI. Mn is a nominal bending moment resistance. Mu is a factored applied moment. S is a spacing of reinforcing bars. Vc is a nominal shear resistance of the plain concrete section. And Vu is a factored applied shear force. We also introduced Wd and Wl as a dead load and live load respectively on the floor, which has units of pounds per square foot. Phi is a resistance reduction factor, which is 0.75 for shear and usually equal to 0.9 for bending, as explained later. And rho is a steel ratio, which is AS divided by BD. Design equations. The design equations are identical with those in a singly reinforced rectangular cross-section. Please see the video number 7 in this series. Therefore, the nominal resistance Mn is equal to ASFI d minus A over 2, where A is equal to ASFI divided by 0.85 prime sub Cb. Also, if the factor resistance phi Mn is needed, the resistance reduction factor phi must be determined. It is usually equal to 0.9. However, as explained later, it depends on the strain at the tension steel, as in the case of beam design. Also, as in design of beams with rectangular cross sections, the parameter R is Mn divided by Bd squared, and the steel ratio needed can be found from the equation 1 over m multiplied by 1 minus the square root of 1 minus 2m R over Fi. And again, rho is equal to As divided by Bd, and m is equal to Fi divided by 0.85 of prime sub c. We use inch and pounds in all of these equations. The value of resistance reduction factor is usually equal to 0.9. However, in general, it is found based on the strain at the location of the tension steel, epsilon t. The smallest value for phi is 0.65 when epsilon t is less than or equal to 0.002. The largest value for phi is 0.9 when epsilon t is larger than or equal to 0.005. For the strain values in between the 0.002 and 0.005, that middle transition equation is used. The equation for epsilon t is given as 0.003 times d minus x divided by x. And x is equal to a divided by beta 1, where beta is equal to 0.85 for a prime sub c of 4000 psi or smaller. However, it is reduced by 0.5 for every 1000 psi over 4000 psi prime sub c. The smallest possible value for beta 1 is 0.65. Design requirements. Design requirements listed here are especially those that are different from beam design. Number 1. The protection cover is 0.75 inches for floor slabs. Number 2. Although shear reinforcement can be used, generally slabs are designed without shear reinforcement such as stirrups. Therefore, D is simply equal to H minus 0.75 plus 0.5 dB, where dB is a bar diameter. Also, D is the same as D sub T. And here is a detail showing how D could be computed based on h and diameter of the bar. Number 3, because 1 foot of the width is used, all design quantities are described per foot values. Here are the units used. For factored applied moment mu and nominal bending resistance Mn, the unit is foot-pounds per foot. For factored applied shear Vu and shear resistance Vc, the unit is pounds per foot. For the area of tension steel As, the unit is square inches per foot. Number 4. In design drawings, the steel bars are designated in terms of their spacing. For example, the steel may look like this. Number 4 at 6.5 inches on centers. It is a good idea to select the bar size first and then do the calculations for determining the required steel ratio ρ and the area of steel As. Number 5. The minimum amount of steel must be satisfied for both the main reinforcement and in the perpendicular direction. The equation for minimum amount of steel is 0.002 bh if Fy is less than or equal to 60,000 psi. However, if Fy is larger than 60,000 psi, As minimum is larger of 0.014 bh and 0.01 h times 60,000 divided by Fy times bh. Notice that for the minimum amount of steel we use bh and not bd. The alternative minimum steel used in beam design, which is 4/3 of the required As, is not acceptable for a slab design. Number 6. Bar spacing S cannot exceed 3 times h and 18 inches. A convenient equation for determining bar spacing is S in inches equal to 12 inches times AB divided by required AS, where AB is a cross-sectional area of the bar size selected. For example, if number 4 bars are used for design, which has an area of 0.2 square inches, and if the required AS by calculation is 0.15 square inches per foot, then the spacing would be S equal to 12 times 0.2 divided by 0.15, which is 16 inches. Number 7. As in beam design, the factor shear force for design, Vu, is computed at the critical section for shear, which is at D from face of the support. Number 8. The shear resistance V sub C is computed using the following equation. V sub C is equal to 2 square root of prime sub C BD. If no stirrups are used in the slab, a major factor in increasing the shear resistance in the slab is therefore the thickness H. If lightweight concrete is used, then V sub C is modified. Structure analysis. A detailed structure analysis is needed for continuous slabs with appropriate pattern loading used to arrive at the most critical bending moment Mu and shear Vu. Alternatively, the following procedure can be used for approximate analysis based on certain conditions. Number 1. Simply supported single span slabs. Mu is equal to WL square over 8. Vu is equal to Wu times L over 2 minus Z, where Wu is factored floor load in terms of the dead load Wd and live load Wl with the respective load factors applied. Therefore, Wu is 1.2 Wd plus 1.6 Wl, and Z is equal to D plus 1/2 of the support width. Number 2, slabs on multiple supports. These are continuous systems with identical span length, a minimum of 2 spans present, and the live load not greater than 3 times the dead load. Approximate values for positive and negative bending moments and shear can be found from Chapter 6 of ACI 2014. These values are listed in terms of the factored floor load Wu and the clear span length Ln. For example, for the situation shown, the moments are listed, and this is for a case of Ln larger than 10 feet. In this case, there is an spandrel beam on the exterior of the floor system, and there are interior beams providing support for the slab. This is a monolithic system. The slab is integral with the supporting beams. For Ln smaller than 10 feet, negative moments for all interior spans is Wu ln square over 12 instead of the values that you see listed up there. And for shear, Vu is 1.15 Wu ln over 2 for exterior face of first interior support, and it is equal to Wu ln over 2 for face of all other supports. Notice that Wu is a factored floor load with PSF as the unit. Therefore, all moments Mu have the unit of pounds, foot per foot, and all Vu values have the unit of pounds per foot. A step-by-step design procedure. Step 1. Select the thickness and bar size for the slab. The following values from ACI are used in selecting the thickness of the slab for a case of Fi equal to 60,000 psi. For example, for a simply supported slab, the minimum thickness for the slab is L over 20. For Fi values other than 60,000 psi, multiply the values in the table by 0.4 plus Fi divided by 100,000. For a slab made up of lightweight concrete with a density Wc equal to 90 to 115 pounds per cubic foot, multiply the values in the table by the greater of 1.65 minus 0.005 Wc and 1.09. Usually, smaller size bars are used for floor slabs, number 3, 4, or 5, and larger sizes, number 6 and 7, for thicker slabs, especially those used in buildings. In other words, in bridges, not buildings. Step 2. Conduct the structural analysis and compute Mu and Vu values. Step 3. Compute D as H minus 0.75 plus 0.5 dB. Step 4. Assume phi is equal to 0.9 and compute R based on Mn, which is Mu divided by phi. R is equal to Mn divided by Bd squared, where B is equal to 12 inches. And remember to use inch and pounds in that equation. The unit for R would be PSI. Step 5. Compute the required steel ratio and area of steel needed from this equation. Rho is equal to 1 over m times 1 minus the square root of 1 minus 2mr over Fi, and As is equal to rho Bd. Step 6. Compare As with As minimum and adjust As if it is less than the minimum. And remember, As minimum was 0.002 Bh if Fy is less than or equal to 60,000 psi, and if it is Fy is larger than 60,000 psi, then As minimum is a larger of 0.0014 Bh and 0.0018 times 60,000 divided by Fy times Bh. And again, notice that As minimum is computed in terms of Bh. Step 7. Once As is finalized, compute the spacing between bars S and make sure the spacing is within the limits. The equation for S, as given before, is 12 times AB divided by required As, and it cannot exceed 3H and 18 inches. Step 8. Using as used, compute A, X, epsilon T, and Phi, and make sure the available bending resistance Mn is adequate. The sequence of equations is given in the next slide. The equation for A and X and epsilon T. Nominal resistance Mn is ASFI D minus A over 2. And the factor resistance phi Mn has to be larger than Mu. Step 9. Assuming no stirrups are used, check the shear. If a shear is not satisfied, to do the following equation: increase the thickness or add stirrups. V sub u has to be smaller than phi v sub c, which is phi 2 square root of prime sub c bd, where b is equal to 12 inches and phi is equal to 0.75 for shear. Step 10. Use minimum steel in the perpendicular direction and provide a detail of the reinforcement for the slab using one of the three details given before, which is also we give them in here again. Limitations and other design considerations. The value of a square root of prime sub c cannot exceed 100 psi in computing V sub c unless the minimum shear reinforcement is used. As indicated before, generally slabs are designed without shear reinforcement. Therefore, this limiting value for a square root of prime sub c mostly applies. A minimum shear reinforcement is needed in areas in the slab where V sub u is larger than 5V sub c. This minimum amount follows the same minimum value used for beam shear design. For those, please see lesson 8 in this series. The location of the critical shear, just like beams, is at D from face of the support if the following conditions are satisfied. The reaction in direction of applied shear produces compression at the end of the slab. Loads apply at or near the top surface of the slab. No concentrated load applies within D from face of the support. If the slab is integrally built with the support, VU can be computed at the face of the support. Here is an example. In this example, we would like to design reinforcement for a slab system with L equal to 14 feet. The slab is continuous and non-monolithic with the supporting beams as shown. The loads are as follows. Live load is 75 psf, dead load is 15 psf, and this is in addition to self-weight of the slab. If prime sub c is 4,000, Fi is equal to 45,000 psi. Therefore, the parameter m is 45,000 divided by 0.85 times 4,000, which is 13.235. Because the support width is equal to 12 inches, therefore Ln would be equal to 13 feet. The exterior span has one end discontinuous. Using this span as a basis for determining the slab thickness, from the table given for minimum h, we find out that the minimum h has to be L over 24. Turns out this value is 7 inches. So if we select 7 inches as the thickness for our slab, we can now compute the self-weight of the slab. 7 divided by 12 to convert the unit in feet, multiply by 150, which is the density of concrete in pounds per cubic foot. The result is 87.5, and the unit would be pounds per square foot. The total dead load, therefore, is 102.5, and now we can compute WU using the load factors. We ended up with 243 pounds per square foot. From Chapter 6 of ACI 2014, the moments are obtained and shown in the following figure. Notice that the moment at the end is 0 because that's a free end. There is no integral support there. The maximum negative moment is WU ln square over 10, and the maximum positive moment is WU ln square over 11. Putting the numbers in the equation, we get the mu negative. The maximum value is 4,107 foot-pounds per foot, and the maximum positive moment is 3,733 foot-pounds per foot. And shear would be equal to 1,816 pounds per foot. This is the maximum shear. We select the number 3 for this steel. The diameter of number 3 is 3/8 of an inch, and the area is 0.11 square inches. Therefore, we can compute D, which is 6.06 inches. Next, we find out the amount of steel needed. For the negative moment, we assume phi is equal to 0.9. The required Mn, which is mu divided by phi, is equal to 4,563 foot-pounds per foot. Plugging that equation in R and watching the units, we use inch and pounds, we end up with R equal to 124 psi. Now using that value in the equation for rho would be equal to 0.00281. Therefore, the required area of steel is 0.00281 times 12, which is B, times D, which is 6.06. The result is 0.204 square inches per foot. Now let's compare it with AS minimum. AS minimum is 0.002 BH. So it's 0.002 times 12 times 7, and we get 0.17 square inches. Certainly we should be using the value that we computed, which is 0.204 square inches per foot. Now plugging that in the equation that we had for the spacing, we get the spacing has to be not greater than 6.5 inches. However, for practical reasons and simplicity, we recommend using number 3 at 6 inches on centers. So it's a little bit more steel than we need. Actually, we are using 0.22 square inches per foot. That's the amount of steel being used. So we use that one in computing A, which is 0.24 inches. From that we get X, which is 0.28 inches. From that we can get epsilon T, which is 0.06, a very large value compared with the upper value for epsilon T of 0.005. That means that phi certainly is equal to 0.9 as assumed. Now we compute the factored capacity phi mn. Using the equation for phi mn, we end up with 4,410 foot-pounds per foot. Certainly this is larger than mu, therefore our design so far is okay. We repeat the same calculations for the positive moment. Required positive moment is 4,148 foot-pounds per foot. Plugging that in the equation for R, we get R equal to 113. The steel ratio is 0.0026, and the required area of steel is 0.19 in this case, square inches per foot. Compared with the minimum amount, we use 0.19, and that gives us a spacing not greater than 6.9 inches. And for the minimum steel in the perpendicular direction, if we use a grid at the top and one at the bottom, then we need to divide the minimum area of steel needed by 2. So we need to have 0.085 at the top and bottom. Again, using the equation for the spacing, we get 15.5 inches if you use number 3 bars. Therefore, for simplicity, this is what we suggest. Use number 3 bars in a grid of 12 by 12 inches at the top and bottom. This is like a base grid. In the span direction, we add number 3 at 12 inches on centers over the support and at the mid-span over a length equal to L over 2, which is 7 feet. Since there is already a grid of 12 by 12, then the total steel provided over the support and at the mid-span will be now number 3 at 6 inches on centers. Certainly that would meet the design requirement. Now we check for shear. Recall that V sub u is 1,816 pounds per foot. The shear resistance is phi V sub c, that's the factored shear resistance, and then phi is equal to 0.75. We end up with 6,899 pounds per foot as shear resistance. And certainly this is larger than 1,816 pounds per foot, so therefore shear is okay. And here is a reinforcement detail. We use 2 grids, one at the top, one at the bottom, number 3 bars at 12 inches on centers. Then when we need additional steel, we add additional bars. Number 3 at 12 inches on centers shown at the bottom with dashed lines in the mid-span, and number 3 at 12 inches on centers shown with solid bars over the supports. Therefore, the spacing of the bars in those areas with additional steel is now reduced to 6 inches. And therefore, the available steel would meet the required amount of steel by calculations. The example provided is a case of cast-in-place slab. The methods presented are also applicable to precast slabs. However, please note that the slabs that are precast and pre- or post-tensioned with tendons are different and designed using the procedures that are applicable to pre-stressed concrete. Thank you for watching this video.